Hello everyone, we're doing lab 9 of the real-time physics integrated into the IOLab. Okay, so I've already opened the IOLab software. Let's go to our lab 9. Hmm, okay, okay, so lab 9 is work and energy. So we'll see when the work is done, what the physical work depends on, what does it depend on, like force, distance covered, and what relationship of work and energy. Okay, so this one we'll see. We go and read through this one. You can write your name and move on. Do not forget to click on save and go next in the bottom of the slide when you are done. Okay, done with the slide. You can write your name, and I've already connected the dongle. Okay, so the concept of physical work and power. So we have in this one the three cases are given, three scenarios are given. So we'll choose the one when minimal work is done. Okay, that's the one. So yeah, you have to lift something you at 20 feet. Okay, 100 bucks of 50 pounds and 50 bucks of 100 pounds, so you have to 10 volts. So and there is, you can see the difference, there is some angle is there. Okay, in this case, so you are moving a longest distance, but you are applying a force at some angle. So this, you may see like how you can predict how in which one you will be giving more less work or less effort. Okay, or power, you have to apply less power, less effort. So you may go ahead and make a prediction and then click on save and go next. Okay, as the real-time physics idea, you will predict first, do the experiment, see, and then move on to the next one. Okay, go ahead, predict your answers, and then we'll move on to the next slide. Okay, in the next slide, let's do the experiment. Okay, so we need two heavy books of approximately same weight as they have given, some meter scale. So you have to notice like your effort. Okay, so how much effort you'll put in. So lift one of the books at slow and constant speed from the floor to the height of around 1 meter several times. Note the effort that is required. So you can take one book, okay, lift it slow and steadily at the same speed to around 1 meter. Okay, you can measure the height you want to lift. So like something here. Okay, slow and steady. And then in the next one, push, repeat this time lifting two books. Now I lift to the same, they are approximately same weight. Okay, I'm measuring the effort that I need also. The same slow and speed, same speed, but to the same height with two books now. Okay, with two books now. Okay, I can lift it. Then push a book 1 meter along the floor at a constant speed. So I'll start to put from here. So let me push it around here. Okay, so let this be the starting point, something like this. I'm pushing it slow and steady. Okay, one book. Let me notice the effort. Okay, to some distance. Now I'll push to the same distance. So two books, they are of similar weight. Okay, same distance, same speed. So I'm noticing the effort as well. So you can do that. You can use one book, lift it to a certain height. Two books, lift it to the same height. Notice your efforts when moving to one book pushed to a certain distance, the initial distance. Okay, two books pushed to the same distance. So in each case, lifting or pushing, why must you exert a force to move the object, extra force to move the object? So when we use two books, the mass was increased because of the mass. Okay, how much effort does it take to lift or push two books instead of one? So if you have noted, it should be twice. Okay, if you, so based on that, you may give your answer. Same thing for here. How much effort does it take to push or lift twice the distance? So you can give the answer. If you define work as effort, how would you say they depend on the force applied and the distance moved on? Okay, so when the effort that we applied was increased when we moved to the higher distance, yeah, when we push to the higher distance, or when we lifted to the higher distance. So it has to be directly related to the distance. And the next question, the force applied was increased when we increased, like when we had more effort, when the force we need to apply was increased in both cases. So you may give an answer. So effort has, or work were defined as effort. Work should be directly related to the force and the distance. Yeah, this work should directly depend on force applied and the distance moved. So yeah, based on your experiment, you can write your answer. Okay. So after finishing the slide, click on save and go next for slide 3. And in the next slide, so they have given physical definition of work. Okay. If a rigid or rigid object or point mass experiences a constant force, okay, along the same line, so it means there is no angle, the angle is zero actually. It's just with the force applied and the direction of the motion of the object. Okay, so in the same line as its motion, work can be defined as this: force times the displacement. Okay, force times the displacement. That's the so in order for the work to be done, there should be an force and there should be the distance applied. Okay, so distance, there should be some displacement. So this definition of work with the amount of effort you had to extend when you moved books under different conditions. Yeah, I think when the force was changed, work was, effort was changed, increased work. Yeah, delta x, when the distance moved was changed, this was changed. So yes, so they agree with our previous. Does effort necessarily result in a physical work? So in order for there to be a physical work, which is definition is this one, there should be some displacement. Okay, so if we make an effort, does that necessarily means there is a physical work? Like I'm making an effort to move this book. Okay, what is this move? I'm just applying some small force. Okay, so there is a small effort, but the book is not moving. So but there is no displacement. Yeah, so that means you might have clear idea. So when if for this, in order for the effort to result in a physical work, this there should be some displacement as well. Okay, without displacement there cannot be physical. Like in the tug of war, if nobody is moving and they are just applying the effort, there is no displacement there. So if no movement is there, so there is no, without displacement the work is not done. So effort does not necessarily result in a physical work. Okay, for the next experiment, when the force is applied and displacement lie along the same line. Okay, so when can work when the force and displacement, when the applied force and the displacement lie along the same line. So what we need is the inclined ramp, the IOLab. Okay, inclined ramp between 15 to 20 degrees. IOLab with some weight attached to it. So they have suggested to keep the IOLab. Is that taping use software? No, I think yeah, taping the book or another mass object of the same IOLab over the single wheel, like they have done it here. I have used the water bottle. Okay, so but okay, something like this. I have taped it here. Okay, single water beer. Make sure your wheels are moving. Okay, while taping. Yeah. So we have to make an inclined ramp around 15 degree. So let's use this one. You can make 15 degree here. Okay, you can use a protector to measure. And then let's turn on the IOLab. Okay, okay, it's connected here. Yeah. After that, they want just okay. I think this part is done. So it is important to zero the force sensor on the IOLab with nothing pushing or pulling. So right now, I left it here. So force sensor is here. Yeah, there is no force applied in the sensor. It's just left out. So let me zero the force sensor. Okay. Now they want us to pull it at. Let me pull it from here. Okay. So let's keep it like this, and then find the force needed to pull the IOLab and book means we have used some weight here of the ramp at a constant velocity. Begin the graphic force and the displacement as function of time. So we can do that. Pull the IOLab. So the string that we have used is always parallel to the ramp. So it has to be parallel with the ramp. Okay, and we will try to maintain a constant velocity also. Okay, so what you can do? Let's record. Okay, let's make it parallel, record it, and then I will pull it, try to make it slow and constant. Okay, if you are not satisfied with the run, you may repeat it again. We always know that. Okay, so okay, let's zero the force sensor without any force being applied again. Now I want to add the run. Okay, let's zero the sensor. Okay, now let's Same technique. You want to make it slow and steady, constant velocity. Yeah, record it, try to move it slow and steady, slow and steady, slow and steady. Okay, so we have to find a reason where the force is constant and velocity while moving. Okay, while moving when the applied force is constant. So if we see here, you can take that reason also. So this was the reason when the IOLab position is changing means IOLab was moving. Yeah, it was zero means it was not moving until here, although the force will be applied. Okay, so constant force applied during this region. Okay, so we can take one of them. So do you want to give first or second? Anyone would be fine. Okay, so let's remove the. I can work with anyone. Okay, let me do the first one. Okay, so it seems the constant force around here, this region here. So we have to see where the IOLab is moving. Also, while it was moving from here to here, kind of force constant is again start from here also here to here. Okay, in that region, you have to see velocity was also kind of constant. Okay, this region would be okay. So you can, they want us to take the averages of the force in the y direction pulling parallel to the surface. Okay, that is in the y direction. Okay, so let's see, you can, we already know you can use this tool. Yeah, so we'll try to see a reason when the IOLab was moving and the force was approximately constant. Okay, with the velocity being constant as well. So we can take this reason. The IOLab has to be moving. Okay, it's increasing, but okay, I think that should be. You can take it, go up to here also. That's fine. Okay, when the IOLab was moving and the force was approximately constant. In fact, you can discard this also, but that's okay. So you may write your average force. Okay, it will be different for different person. Okay, like I might have used higher weight on the laptop. Okay, and the velocity that I have moved might be a little. Um, so based on that, it will change. So the weight that I have used might be different. After that, you may write your value here. Okay, do not. So I just did what it is said here. So we have to be careful in this experiment. While moving, this one has to be parallel here. Okay, parallel during the whole movement. And selecting your region of interest, that's also an important thing. So we'll select region when the IOLab was moving and the constant force was being applied, meaning moving with the constant velocity. Okay. Okay, now we'll apply force at some angle. Okay, it has been set 45-degree here. So when the calculating work when the force and displacement lie along different direction. Okay, so let me turn on the lab. You can do your prediction in when is larger force required. Okay, will the force sensor measure the same force or a larger force when we apply the force at some angle? Okay, like we did it parallel last time to the ramp. Now we'll be making some angle and doing it. Okay, that's the whole goal. Okay, I have turned on my IOLab, so let me zero the sensor. Yeah, without any force applied here. Okay, zero the sensor. Now let's, as it has been said, we have to make 45-degree. Yeah, sorry. So 45-degree to the surface of the ramp. Okay, so let's see. So we'll make a spring. Okay, okay, same length of the string. Okay, 45-degree. Okay, and then while moving, it has to be 45-degree throughout. Okay, you can use your protector also. Let's record it. We'll try to maintain the same constant speed and 45-degree as well. Okay. Okay, I think it took some time. So the way the well, you think velocity was not same, match with the angle, you may. Okay, let's add on. Yeah, we can add on always. Zero the sensor without anything being pulled. Make it 45-degree. Okay, something like this, 45-degree, and some string. Now I can record it. Okay, try to make the velocity same like before, making it 45-degree. Move it through. Okay. You may repeat the experiment if you want. Okay, you may repeat the experiment as needed, but we need to have same, what's it called, same rate of change, so like same velocity. Yeah, so let's see if we can remove this one. Okay, so the velocity seems to be, if you want, like, you can try it again. Okay, if you want to make it exactly similar. Okay, your choice. Now in the force, let's see, when it was almost constant, velocity was almost constant, and force was constant from around here to here. Yeah, so we can take that reason to take the average. So you may go ahead. So if you want, you can try to make the velocity more similar if you want. Okay. Okay, it was kind of constant here. Okay, you can repeat the experiment with your choice. Okay. So let's see. I have to make constant from here to here. Okay. So kind of constant from here to here. It seems similar, but you can always repeat it. Okay, if you want. Okay, I repeated the experiment again. Okay, and then so that we have to make, like, we wanted to move with the similar constant velocity, yeah, same speed, and we wanted to see the force. Now we can take the average again. So you see, when we are applying, okay, so velocity is kind of same, yeah, in the, or if you want, so we want the force to be constant, yeah, and the velocity to be similar. So based on that idea, let me do it again. Okay, so if we can compare, the velocity is kind of similar. Okay, the force, we can measure it 0.4 Newton. Okay, so in my case, it will be a different for a different person. So you can repeat your experiment. Okay, so the constant velocity, we want it same, like same, and so slow speed like what we had, 0.929, around 0.29. Yeah, and that there was some constant force involved. So we wanted to move around same constant velocity, but at this time the difference was we are moving with an angle. Yeah, like there is an angle. Yeah, 45, around 45 degree we moved with an angle. So after that, you may write your answer 0. You may write your average force. Okay, hold on, this is the same one. Okay, so after that you may write down. So you have to be careful while rezeroing the sensor. Okay, I think I'll show you a trick so that that can help you. So okay, while rezeroing a sensor, we said there should be no force applied there. Yeah, that's here. You can see here. Okay, so there is no force applied. So someone may want to just click on rezero directly. But what I would say, what you can do is, like, you can add run. Okay, record it. Okay, so it's measuring right now 0. That's fine. Okay, you can stop it and then click on rezero sensor if it is measuring 0. Otherwise, like, you might um, somebody might select some reason, like when for the previous one, if you rezero sensor, this will take that point to 0 down. So what you can do every time, if your sensor has not been rezeroed correctly, to check that one, what you can do is you can just record some, add on. Okay, record something. Okay, and if it is 0, that is fine. If it is not 0, then what you can do, then you can click on rezero sensor after that without applying anything. Okay, and then it will go back to 0 and it will come back to the right place. Okay, so I think that is not of interest right now because we missed on this one, so that's what I was worried about. So let's see, the velocity around same, force around similar. Yeah, so 0 0.2, I think we can take this one. So it is 0.741. So it will be different for different person. Okay, 0.741, because you might have, you might pull a different constant velocity. It was 0.28 for the previous one. That's why I use this one. So main concept is you will use a similar constant force that has been applied. You will note that value. Yeah, this is for the second one. Okay, be careful of that. So 0 point, so you may write, you might have a bigger difference also. So then you may note down this value here. Does it seem to take more effect to the IOLab and when the mass was inclined at an angle? Did the angle at ramp? Okay. So you may go ahead and answer your answer based on your calculation. Okay, it seems so. 0.74. It was how much in the previous one? 0.6 something. Yeah, not much difference, but at least 0.66 and there is 0.74. So you may go ahead, write your answer. Okay, based on what you see. Okay, after writing the answer, you may go and click on save and go next. After that, so they have given the definition of force. Sorry, work with the angle, the cosine of theta. Okay, theta is the angle between the displacement and the applied force. If the force component, if it is the force component parallel to the displacement, that is included in the calculation of thus when the force and displacement are not parallel, then we may use this equation. Yeah. Do your observations support this equation as a reasonable way to calculate the work? So you can see your calculation, your work, and based on that, you may decide, okay, for the calculation. No. So based on all your observation in your choice of prediction 1-1, was that right? Did it require less work? And the definition of power is given here. Power is rate of work done per unit time. Yeah. So what is the rate of change of work done? Is it amount of work done per time interval? So that will give the power. Okay. You may go ahead, write your answers and click on save and go next. Okay. Make sure you write the answers. Okay, in the next one, we'll see work done by constant and non-constant forces. So we'll need the IOLab with the force sensor calibrated. We already have it. Smooth board or other lab surface, we have it. Meter stick, spring on stress length about 7 centimeter. I think it comes with our IOLab box itself. Okay. So, okay, work done by a constant lifting force. In this activity, we will measure the force done by when you lift an object from the floor through a measured distance. You will use the force sensor to measure the force and the wheel to measure the distance. Okay, set up the ramp as shown. So you have to keep it like this now. The picture, you will be the most vertical against the wall or table. Roll the IOLab along the ramp positions almost vertically so that wheels stay in there. So we have to make sure this wheels is in contact. Okay, practice lifting the IOLab by the string which is attached to the eyeball is getting to the force sensor. Okay, for the next slide, when lifting done by a constant lifting force. Okay, so the IOLab is down here, so you make a wire longer so that you can put it like this way. Okay, and we lift in such a way that it's always in contact with the IOLab. Okay, sorry, in the ramp. Okay, the wheel has to be contact in the ramp. So let there be nothing lifting that IOLab. There's the sensor without anything over there. Okay, then what do they want is click record with the IOLab resting on the ground. Now lift the IOLab at a slow and constant speed to a distance of about 0.5 meters. So you may use your square meter tape to make it around 0.5 meter. Okay, your choice. So see around 0.5, then we can. Oh, our IOLab is off. Okay, so let's turn it on. Okay, now I should be able to record now. Let's rest it here. Okay. Okay, we have to lift in such a way that the wheels of the IOLab will always touch this ramp. Okay, so you can make a little bit tilt if you want. Okay, so click on record and lift the IOLab at a slow and constant speed through a distance of about 0.5 meter. Okay, I have to turn in the IOLab again. Turn it on so that I can record. Okay, now let's. Sorry about that. Okay, keep it there. Now I have already zeroed like before it started. If you want, you can do it again. No force being applied. Reduce the sensors. Down. Okay, and then okay, ready to be filled. Following this step here, I'll click on record. Okay, and then I will lift it slow and steadily to some around 0.5 meter. Okay, so we have to make sure the velocity is constant. If you let's do it. Oh, if you want to do it again, we can same thing. Do it again. Add run without pulling anything. You may re-zero the sensor. Okay, well, I've just left everything down and then re-zeroed. Okay, and it like this, record, and lift it again. Okay, I might have to re-zero the sensor if I did not do it. Oh, that's fine. Okay, yeah, the trick that I showed, if you, okay, let's keep it like this. Okay, add on. If you want to re-zero, you can just click, like you can click on re-zero without putting anything on it, but to be sure, you can click on record. Okay, that's now in zero, that's fine. You may stop if, then you can click on re-zero sensor. It was in zero, that should be fine, then that should not be a problem. Okay, let me remove the last one. Then let's record it. I'm doing it for the last time. Okay, no force being applied, record it. I will lift it to the slow and constant speed. Okay, that's always okay. Then that should be done. Mm. So this will change the position, yeah. So you may keep whichever you want. Okay, I think I can go with the last one or anyone you like. So the one you are satisfied with. So this was the time when we were lifting, yeah. The position was changing. I was changing there, and let's see. So did the force needed to move the mass depend on how high it was off the floor, or was it reasonably constant? So you can compare your position and force. So this is the position where it started to move. The position where we are lifting here, this is the height being changed, and that's the force being applied. Is it changing, or is it constant reasonably? So you may answer the question. Velocity is kind of constant. You can see slow and steady during the motion. So using the analysis feature of the solve rate, average mean force over the distance, the mass was lifted, record this force and distance below, average force and distance lifted. So distance is distance lifted will be the highest point, yeah, because you can the average force. Okay, so if you are not seeing clearly, let me auto scale. So it goes up to 0 0.4. Yeah, let's do it from 0 0.5. Will that work, or 0 0.8? No, it's still not working. Okay, let it be 1. Okay, that should work. 1 to -1. We don't need -1, but it's still okay. So the maximum, like the distance lifted is the maximum height that it has moved. Yeah, it was at 0 height, then we changed the distance and it went up to around RY. The maximum is 0 point something, 0 0.47. Yeah, around 0 0.47. Yeah. For me, for you also use the similar concept, and the force is average force is for the motion only. Okay, so when you move from here to here, so you can select from this here. Okay, how you know how to take the average? Yeah, first let me remind you, have to click on this icon, then you select the region you want to take the average of. Okay, so based on the first, oh, we want to know IOLab motion, so we'll select from up to the around whole thing. Yeah, around that's okay, that should be okay. Or you can select up to this also, the maximum point. Okay, starting from around 0 to around the maximum. Okay, so what is the average force? So these constants, yeah, there are different constants. So 1.97 Newton. Let me go ahead, write your answers. Okay, full and position graph. So does it depend on height, the force? Yeah, as I've already said, the height is changing, is the force changing, or is it constant? You may answer that. You may write this average force, and the distance lifted is the maximum height here. Okay, you have raised. And then calculate the work done in lifting the mass. So what is our equation? So you already know, you have cosine of theta times delta x, but where the angle for the force applied and the displacement direction of the force applied and displaced is in the same line. So we can just use f times delta x, distance covered. So average force times distance cover. And we multiply these two and get your answers. Okay. After writing, you can click on save and go next. Okay. After writing the answers over here. Okay. After you have written the answers and click on save and go next. In the next slide, so they want us to give the plot for force versus the wheel. Okay, so if you see here, what is the time from around 1.5 to 3, or we can say 1 point, the force is constant, yeah, when the position is increasing. So they want us to put plot force versus wheel. So using this symbol parametric plot, and click and drag the data below force versus wheel plots to the relevant quantities Force times distance is also the area of rectangle under the curve. Okay, so let's click on this one. So I clicked on this one. So they want us to select the relevant data. Okay, so if you might don't get confused. Okay, I think the direction is just reversed from this graph to here. So you see, so we had constant from, if you see here in this graph, you see there was kind of constant. Yeah, it was constant and it changed. It started like it was zero in the beginning. It was zero. The position was zero until 1.2 or something. So it has to start no 1.2, 1.3, 1.4. Okay, 1.4 to 3.1 or 3.2. Okay, so the 1.4 to 3.2. So if you see here, so this is just in reverse direction. It was kind of constant. Position was constant. Yeah, and it is begin to change from here. The position started to increase. This is just shown in the negative direction. That's it. The magnitude is increasing. If you see this, take it as zero. This has a time. Okay, position was constant. Sorry, position was zero in the beginning. We now change, and it started to change. We lifted, yeah, and the position increased, and it became maximum around this up to this point. And the force was kind of constant when we were lifting. Yeah, the same graph for here from 1 point something to 3 point something. Yeah, same region. So we'll select that region in that graph. Okay. So as indicated, sorry, this one. So yeah, sorry, this one. I click here. Then we'll select the region that is relevant. So this is from around here when it started to change. Yeah. So kind of here. So you can select up to when it became maximum. Okay. Not after that. I think around here will be okay. Okay. Then it says force times distance is also the area of rectangle under the graph, position graph. So one can find the area under the curve by counting the distance. So you may count these squares here, but it might be difficult also. Yeah. So counting the squares, calculating the counting of this. So the area, the area here, the area of this rectangle. Okay. This one will give us the work done because force times distance is the area. Sorry, yeah, is the work done, and that is effectively the area. Okay. So the area of the rectangle, like here, you can see one rectangle is formed. This will give us almost. This will give us our work done. Okay, the area of the rectangle formed. Then you can click on save and go next. So you may find the area by counting the squares, yeah, as it has been said. Or what you can do is you can just find the area of the rectangle. Okay, area of the rectangle, that will also do. If you are not able to count the squares, okay, like this is a rectangle here. Yeah? Force times change, sorry, force times change in distance. Okay, 0. Minus 0. You can just take the 90, 0.43 times the force 1.9. Yeah, so but you can do the difference also from here to here. Okay, now work done by a constant string, non-constant string force. So that was constant force that like when in the previous case. Now we'll do with a non-constant force. Okay, let's make a setup as shown in the picture. So use the clip. Is it here? Okay, then let's use a pencil or pen so that I can hold it. Okay, and then we'll use the string one side. In the meantime, I can re-zero the sensor here. Okay, re-zero the sensor. Okay, then we can put it into the IOLab. If you want to increase the height, you can use the pen instead of the pencil. Okay, you can hold this one for sure. Or if I want to make it as parallel, okay. And then re-zero the force sensor. We just did it. Begin graphing force and position as the IOLab is moved, so that the spring gradually stretches equilibrium length with no force pulling on it. 0.02 by around 0.2 meter. Okay. So we can click on record, then gradually pull it. It's a 0.2 meter, but we can up to us. Okay, did I do up to 0.2? Okay, not exactly. You may repeat it again, yeah. As you already know, you can add on. So nothing pulling or pushing. We can raise it. Not fall, not fall. Okay, you can raise the sensor. Okay, then record it. Then slowly push it. I think I did it fast, but that's okay. Yeah, it was okay. If you want, you may do it again. Your choice, yeah. So to you. Okay, nothing pulling and losing. Add on. Raise sensor. You can record it and gradually pull it so that it goes to 0.2 meter. Okay. Then as before, do a parametric. So let's keep the last one, or you keep. Okay, so it is started to see like it's in the opposite direction, but it's fine. Yeah? It started to stretch 0 up to 0.2. You can see the force is also increasing. It's not constant as it was last time. Okay, velocity we can. Then we may do the parametric like before, parametric plot. Yeah, so we are interested in. So we will not see the reason of the constant. Okay, you see it was constant until. So we started to change from here. Yeah, kind of where from here 1.5, 1.6 to. Is it 1. Yeah, 1.6 to around 20. Yeah, then increasing up to this point. Yeah, 3.7. You may see. Okay. And then you can do the parametric plot, or you can see from here around 1.6, or you can select data from here, yeah. Around 1.6 to 3.3. Is it, what is that? 3.7 around until it becomes position. I am looking at the position, yeah. It becomes constant around here. Around here. Okay. So calculate the string constant from get the slope as a function. So can we get the slope? I'm not sure if we can use. Yeah, okay. So it says slope will give the string constant, yeah. So based on the previous graph, oh, I don't know. How can we select now? Oh, okay, you can calculate the string constant from the graph area, slope of force versus the function. So that's force versus the position, yeah. So you can find the state. Slope is rate of change of time, yeah. So you can take a point here, right, measure the value of force and measure the value of force and position here, measure the value of force and position here, then this force at that like rate of change of force. I mean, take this point, find force and position here, note down force and position here, note down force and position here. Then F2 minus F1 over P2 minus P1 means force here minus force here divided by position here minus position here will give you the slope, and that's slope. That's the string constant. Okay, you can do the calculation, compare this position versus time to one you got in the mass string that was constant like a rectangle. Yeah, it was a straight line in that case, but here a slope line. Can we use the equation calculating the work done by a non-constant force? So for the non-constant force, it is not an average constant force, so we might not be able to use that relation. Yeah, which we are not able to use that because force is not constant in this case. In the previous case, force was constant. In the previous case, when we use this tool, yeah, I'm just showing it so that you may see, you can see the force was kind of constant, yeah, force versus position, kind of constant, but in this case, force is, what is that? Okay, I might have to do it again, but that is not constant, yeah, in this case. Sorry. It's not constant, so we cannot use directly explain. So I can explain, calculate the work done in stretching the string using the area under so we need to find the area under the curve. Okay, area under this curve, you may count this curve. The area under the curve is like from here to here. Okay, so you have to find this area. You may count the squares. If you want to make a triangle like thing, that is also possible, or if you want to break it into this rectangle, or is it a trapezoid? Yeah, something like this. Okay, find the area, calculate the area under this triangle. Like here the area will be, I'm not sure if you would be able to see it, but The area of in between these two is going to give the done. Okay, this area, the whole area. I'm not sure if you are able to see, but this whole area will give you this whole area. Okay. And then after you doing this one, you can click on save and go next. Okay, do all of this and click on save and go next. Now we'll look into kinetic energy and the work energy principle. Okay, let me read through this one and click on save and go next. Okay, so they want us to use two book, toss one book up in the air and catch it. Yeah, if you throw it faster, will it go higher? Alternate between fast tosses and slow tosses. Notice how much effort it takes to throw it and catch when it moves quickly or so. So you have to vary by yourself. How much effort does it take when it moves faster? And like you can toss it, it comes back to the area. You can throw it higher and comes. So obviously, when you throw it faster, it goes higher and it will take like you will require more force. Yeah, so you may do this experiment on your own. Does the effort needed to stop the book seem to change as its speed increases? Obviously, if you throw with higher speed, yeah, when it comes with the higher speed itself, it will change. Does the effort need to throw the book seem to change as its speed increases? How does it change? The same question. Need to stop the book seem to change as it does the effort needed to stop the book. Yeah, same thing. We stop the book and throw the book. Yeah. So with the high, if you want to throw with higher speed, you will need more effort, obviously. So now two books together. Some rubber bands will help having them together. Compare tosses of one and two books go up to the same to go up at the same speed. So they want us first you they want to throw the book one book at some speed and throw two books at same speed and see how the difference. Does the effort needed to stop two books seem to change? Obviously it's going to change. We already have done that. So the effort needed to throw the two books seem to change as the mass increase compared to a single book. Yeah. So stopping means when you catch it, like it will fall down with certain, when you toss it, it will reach a certain height and come back. Yeah, and how much so throwing and stopping, those are the things being varied. Okay. If it reaches higher height, it will come with higher force, higher speed in your hand. If it reaches lower is compared to the lower height. Okay. So the equation is given by this. You may do the experiment. As I have said, if you want to throw it higher speed, you will need higher force, higher effort. Yeah. If you want to stop something that is coming with higher speed, you will need higher effort compared to the one coming with lower speed. So keeping this in mind, you can do all of this by yourself. Okay, and write your answers. Then you may click on save and go next. Okay, in slide 17, so you want to use to know your mass, and then using this conversion, you can just find your mass in kg here. Write your mass in kg here. That they want you to attach one in of the IOLab, listing to one in of the IOLab, and ready to record your velocity as you walk your IOLab like a talk. So it has to be on the wheel. I think that has to be a careful part. Yeah. So okay, let me see actually. Okay, after that you'll move the lab with keeping it on its wheel. Okay, so you can be careful of that. So at different distances, they want you to measure your velocity when the lab is moving. Okay, hold the lab with one hand and just walk it like a dog. So the main concept is right here, which would have a greater effect on the kinetic, doubling your velocity or doubling your mass. You know the relationship, kinetic energy equals half mass times velocity square. Yeah, so if you double the mass, the kinetic energy will be doubled only. If you double the velocity, since it is v square, it is going to be 4 times. So doubling the velocity will have that. Okay, based on the formula you may explain. Okay, so you may go ahead, do the experiment. I just give the main concept. Yeah, and it cannot be negative. Why? Mass will not be a negative thing. You get it from here, and velocity is in the equation. There is v square, so it's always going to be a positive value. Okay, is it possible to have for this answer? So you may go ahead, do the experiment. Okay, as I've said, click on save and go next. Okay, for the next one, when you apply a force to an object in the absence of a friction, the object always accelerates. Thus, force does the work and kinetic energy of the object increases. Clearly, there is some relationship between the work done on the object and the change in its kinetic energy. Okay, what do you think the relationship between work done and change in kinetic energy? So you can predict, then we'll see what happens in the experiment. Okay, so okay, based on work energy principle. Actually, work done on the IOLab is always equal to the change in kinetic. Okay, so let's see. Measure the weight of the IOLab by hanging it from the eyeball. Calculate the mass of the IOLab from the weight. Make sure you zero the force sensor with no force. Okay, so we can do the experiment. Let's see. Okay, to find the mass of the lab, so let's zero the sensor without having anything on it first. Okay, let's zero the sensor, and then let me record if it is zero. Yes, zero. Yes, that's fine. So I can remove it. Oh, I can stop it first, and then okay, hey, okay, let's let it finish. Okay, and let me remove that zero sensor. Okay, so record it. You can lift it with your hand. Okay, I think we did a mistake. Oh, okay, we did not. Okay, that's fine. So you can get your mask from here. Yeah, actually, let's record it. Record it. It should be zero in the beginning. Then we lift it. This will give us idea the constant weight. Okay, so you can. That is the weight. Okay, in Newton. So and the conversion you already know. It's one. No, hold on. So we have to find the mass. So yeah, weight equals mg. Yeah, this is giving the weight mass times gravity. So the gravity is 9.8. So you have to divide whatever you get here by 9.8. So there you get the average force, which is around 1.96 Newton. Yeah, divided by 9.8, because this is the weight. Yeah, this is giving the weight for force. F equals mg here. So if you want to get the mass, you have to divide by acceleration due to gravity. So 1.96 divided by 9.8 will give you your mass, and you may record the mass of the IOLab here. Okay. Okay, and then they want us to make a setup like 2 2. So I think we already have it. So you so similar setup like this. Okay, this one was in as in activity 2 2. So after that one, set up the IOLab. We already did that, begin recording, and then pulling the IOLab grab string stage around 20 centimeter, and then it is the IOLab. Okay, so let's do it. So we have it set up here. Okay, like okay, then in the rest position. So now we don't need this, the first part. Okay, or if you want, you can keep it, but we don't need this. And reserve sensor with nothing pulling on it. You may confirm it. Record is in zero. Yeah. And then reserve sensor. Oh, let it finish. Okay, I can move it and reserve sensor. Okay, and then as it has been said here, let's do the experiment. They want us to record around 20 centimeter. Leave it. Okay, so let's do it like this way. Let me record it. Let me pull. Hey, sorry about that. Okay, I have to do it again. Okay, you can use pen also. Okay, your choice. So let me make it constant so that nothing is pulling. Let's remove it. Let me see if it's right. That's right. Yeah. Let's remove it. Let's zero the sensor. Okay, click on record, and then let me put it around 20 centimeter. I don't know how much it is, and then leave it. Okay. Oh, it said at least, but oh no, there's the position change. Okay, seems force is changed. Okay. Okay, let's do it next one. Okay, next time. How long is 20? Hey, sorry. I wanted to see how stretched about 20 zero from the unstretched position. Okay, so let's do it again. I can add on. Nothing is being pulled. Let me zero the sensor. I can record it again. around 20 centimeter. Okay, and then move it. Okay, this will be okay. Do they want us to stop for some time? Let me see. We might do it today. Okay. Transition from the release the lab, allowing the string to pull it back at least. Okay, let me do all of three and then we can analyze on that. Okay, let's do the same thing again. We can add ROM. Okay, and zero sensor without nothing being pulled. Then you don't need to catch it if you have used the pen. Oh, okay, something like this. Okay, and let's record. Let's pull it around 20 centimeter and then move it. Okay. We may use any of these. Okay, let's use the rice one. You may use the first two also. If you want to do it, you can do it again. Okay, your choice. Okay, so let's do the analysis now. Okay, so what is the time when you release the IOLab? So we stressed it, yeah. Position was being changed to stretch state. So the time it was released, it was increasing. So you have to say when it reached the maximum position, we release it around here, yeah, down here. And then what is the time when it reaches the zero position? So zero position is where? So this is the zero position right around here. So this is your zero position. Okay, that's so this is when it was released. Okay, it had some velocity, you can see. Or if you no, when you release it should be zero. Yeah, the maximum position was here when you release at that time. You left the IOLab. So when you left it, it was just stopped. The velocity was zero. Now when you reach that position, that's no, sorry, zero is where zero. You can see when the IOLab turned back to zero. Yeah, position is zero. It is saying what is the time IOLab reached the zero position. So zero position was this one. When it returned back, it went to zero at that position. Okay, you might in your graph you might not have this, but if you have it also, that's fine. So make sure you see this was when we were stretching, the position was increasing, this became the maximum, and then we left it from here. So this is the time when you release the IOLab. Okay, so make sure while doing your graph, when analyzing your graph, see that this is when we started to stretch, and this is the time when we left it. Okay, that's the maximum position. We released it, the first one answer here. What is the IOLab's velocity at that time? So you'll see this time. What is that time? Okay, maximum, yeah, I think that's the one. So that's around zero. Yeah, 0.8 0, you can write. After that, when we reach zero, sorry, so this was the release time when it is maximum. Okay, when it was maximum, it should be zero actually. Okay, around zero. And then when you reach to zero position is right around here. So that's here. Okay, so you can write your velocity over here. But that's the time when the IOLab reaches zero position and your velocity here. So change to the force versus position graph parametric plot as we have already done, yeah, and drag relevant. So we will go to the relevant, calculate the value of the work done by the string by calculating the area under the curve of the force versus triangle. The position good should go from 20 centimeter to zero. The force will go from its maximum to zero as well. Okay, so that's what they are saying. If you see here, that's also going from maximum to zero. Yeah, so this is the position. You see that the force is maximum. You see velocity is zero. So you can turn into the parametric plot. Okay, so force has to go from, so what was the time here? You may refer from there also. Okay, the time from there also. We are seeing the force is position. So it was maximum here. Okay, it went to zero. We'll use the same concept, yeah. Or we can see it from here. When was, sorry, that was the graph. Okay, so the time was from 2 point, how much is that? So maximum was around here, yeah, 2 point something. Time was how much? Not 2.78. It returned back to zero position. 3.1, 2.78 to 3.1. So you may reach that, okay, around here. 2.78 something, or I went far. So maximum to zero, I think this. This is a close call. Okay, that's why. Kind of. Okay, 2.78 to 3.1. So you may like include this area also or this area. Okay, then you can find the area worked on by this frame. We expected a triangle like a graph here, but it didn't happen. But it's okay. Force versus the position. So sorry. Okay, I think that should be it. I think we lost that one. Okay, I think this should be the one. Position was maximum, yeah, and then it went to zero. So from maximum to zero, force also went from maximum to zero. That has to be the area. Then you can find the area that will be the work done. State work energy principle. Okay, how does the work done on the cut by string to the change in kinetic energy? Okay, so for the change in kinetic energy, you can use the equation. Yeah, sorry, not that one. For the change in kinetic energy, so you can find the area from here that will give us the work done. And this is the same graph. Yeah, we'll just use this same one. So in this one, you can have your velocity here somewhere. Is that this one? I think it will be zero, and this one I already explained. Yeah, that's what velocity half mv square, half mv square. So based on these two, and then change in kinetic energy is half mv square at this point, minus half mv square at that point. Okay, and compare with the area that you get from the parametric plot. Okay, so maximum position was here, you left it, it went back to zero. Find the area from this one, compare it with the change in kinetic energy, write your answers, explain it. They have to be similar. Okay, they will be similar, and that will give the work energy principle. And then you can click on save and go next, and that will finish the lab, I think. Yeah, thank you everyone, have a good day, good night, thank you.